It's that time of year when many people get together with their loved ones to prepare and eat lots of delicious seasonal foods. And here at SciShow, that raised an interesting question. Scientifically speaking, is there an optimal way to prepare your food? From frying and baking to zapping and roasting, here are a few scientifically backed do's and don'ts of food cookery, starting with why we need to cook our food at all. Here's Hank to tell you why some foods should only be served well done.
Have you ever been snacking on some sashimi and paused to wonder, why do we eat raw fish but not raw chicken? Really, eating any kind of raw meat comes with some health risk to humans depending on how it was slaughtered, stored, and prepared. But some are more iffy than others because different animals have different microbes and parasites inside them, some of which are really nasty to humans. Fish is on the safer end of the spectrum. It doesn't usually carry bacteria that are harmful to humans, but we do have to watch out for parasitic worm larvae like roundworms, tapeworms, or flukes. If you eat infected raw fish, the larva will mature into worms that can latch onto your organs and cause some serious damage. Sometimes fish is frozen for storage, and if it's cold enough, any parasites or bacteria hanging around will die. But cooking fish is the best way to make sure that all of the infectious stuff is gone. But if your sushi comes from a clean, reputable kitchen, it's probably safe to eat. Now what about other meats like beef and chicken and pork? The bacteria that live in these animals, like strains of Salmonella and E. coli, tend to be more dangerous to humans than any that live in fish. Many harmful microbes live in cattle guts, not the muscle where we get cuts of steak. But beef can be contaminated if a butcher punctures the digestive tract. So steaks might have bacteria on the surface. Usually a good hot sear is enough to kill off any infections, leaving the inside red is fine because it's sterile in there. Ground beef is more treacherous because any germs living on the surface of the meat gets mixed inside. Plus it tends to contain meat from multiple animals, so one contaminated cow means bad news for an entire batch of ground beef. That's why you should probably not order like totally rare hamburgers. They should be cooked all the way through. The meats firmly on the dangerous when raw list are chicken and pork, which might be carrying even more harmful microbes than beef. Infectious diarrhea-causing Campylobacter strains can live in chicken guts, and the crowded, dirty conditions at many chicken farms mean that lots of raw chicken may be contaminated. Pigs, on the other hand, have historically harbored the parasitic worm Trichinella spiralis, although modern farming practices mostly prevent it from spreading. The larvae form cysts inside of the muscle tissue of pigs, so if you eat infected, undercooked pork, some worms will make a home in your guts. So sushi and rare steaks can be delicious when they are prepared safely, but you should always pass on the pork tartare.
So not preparing your food is an option if you're having a fishy feast. But if you're planning on eating a land animal, deep frying might be the safer way to go, as long as you fry the food hot enough and for long enough. And that's not to say that you can't fry fish as well, or eat fried food with your fish, like the classic fish and chips. For the chemistry behind all things deep fried, here's Olivia.
Whether it's donuts, french fries, chicken, or Oreos, fried food is everywhere, and it's delicious. I mean, isn't that why we all go to fairs? Besides making our taste buds happy, deep fried foods also involve some really cool chemistry, from the cooking process itself to the kind of oil and batter you're using. When you submerge a piece of food into really hot oil, a bunch of chemical reactions start happening, cooking your food and giving it that crisp outer layer. Typically, you'll want the temperature of the oil to be around 180 degrees Celsius, but that varies depending on the recipe. You'll know the oil is hot enough when you drop some food in and it starts bubbling. Now, some people might think that that's the oil boiling, but it's not. It's actually moisture boiling off the surface of the food, since the oil's temperature is nearly twice the boiling point of water. As the water leaves the food, two things are happening. First, the food's surface dehydrates and a crispy crust begins to form. But also, the escaping water molecules leave gaps that let oil molecules enter the food, which is what researchers call the oil uptake. In fact, some studies have shown that the amount of oil uptake is directly proportional to the amount of water that's lost. More oil increases the food's fat content, and therefore its energy content, also known as the calories. And if too much oil gets absorbed, you might be left with a greasy mess of a meal. But you don't want to take your food out of the oil too soon either. Otherwise, the outside won't be hot enough for long enough to cook it all the way through. That's because cooking is all about heat transfer. When food is in a deep fryer, the outside layer of molecules is heated up thanks to convection, from the currents of hot oil flowing around. Then all of those food molecules start start bumping into each other and transferring heat energy. So the inside is heated because of conduction. So those are the basics of deep frying food. But there's a lot more that goes into making a tasty corn dog. Like, what happens when you add batter or a breading to the outside of your soon-to-be fried food? Well, batter is basically an extra layer between the food and the hot oil. So the batter is mostly what's getting dehydrated. All that heat transfer is still happening, only this way the food at the center holds on to more moisture and doesn't get too dry. As fish and chips, fried chicken, and tempura lovers will know, a little batter can also let you add more flavor to the food and give it a crunchy textured crust. You can even add beer to your batter to make the crust softer and crispier. That's because the carbon dioxide in beer forms bubbles that fluff up the batter, and foaming agents, which are certain proteins found in beer, keep those bubbles from bursting as fast as they normally would. Plus, the ethanol in beer evaporates faster than water, because alcohol molecules aren't as strongly attracted to each other as water molecules are. This means the batter will dry out faster, so the food doesn't have to be in the fryer as long to get a crispy crust. But one study did show that beer batters do have more oil uptake than water-based rice or wheat batters, so calorie counters be warned. You might also have heard that some oils are better to use than others when frying food. Different oils are made up of different kinds of fat molecules, or lipids, and have different nutritional benefits. They can also affect the flavor of your food because they break down differently. See, every oil has something called a smoke point, a temperature where it starts to create smoke, which can give the food a bad taste. Basically, the heat causes the lipids in the oil to break down and produce some volatile compounds, which are chemicals that easily can become gases. Some of these leave the oil and enter the nearby atmosphere as smoke, but others can enter the food and change its flavor. Corn oil, for example, is made up of lipids with lots of double bonds, also known as polyunsaturated fats, and it tends to break down more easily at lower temperatures. That's because polyunsaturated fats have some weak carbon-hydrogen bonds, which break and set off a chain of chemical reactions that eventually produce volatile compounds. So when you're deep frying something, you'll probably want to look for an oil that has a high smoke point, and most vegetable oils fit that bill. Deep frying food is a lot more scientific than you'd expect. You have to apply all kinds of knowledge about heat transfer and fat content so that your food is actually edible. So treat this as some food for thought the next time you're eating some delicious hot French fries.
Little did we know that there are chemistry experiments being performed in stalls at county fairs across the globe. And baking is all about chemistry as well. Chemistry holds the answer to questions like, if you're out of baking powder, can you substitute baking soda? Well, this next video has the answer.
If you've ever made one of those papier-mâché volcanoes, you know that household acids like vinegar and bases like baking soda react to produce gases, that bubbly lava. But did you know that a similar chemical reaction is what makes cakes and biscuits fluffy? If you see a recipe call for baking soda or baking powder, that's what's helping your tasty baked goods rise. Baking soda and baking powder are just made up of slightly different compounds, which can affect the chemistry of your cooking. Back before grocery stores and fancy cake recipes, if you wanted to make your bread rise, you needed leavening agents from natural sources. And by that, I mean bakers would leave their dough sitting out so that wild yeast from the air could move in. The yeasts digest sugars in the flour and make chemicals like carbon dioxide through a process called fermentation. All that carbon dioxide gas makes the dough slowly rise and create fluffy loaves of bread. Eventually, people started learning to save some of their raw dough, or just some of the flour water microbe goop, to kickstart the process the next time. We still use this method to make sourdough bread today, and without yeast, bread just doesn't have the texture and flavor we're used to. But around the 1830s, bakers started figuring out that they could create a quick chemical reaction themselves, so they didn't have to wait for the yeast to do its thing. That way, other baked goods like cakes and biscuits could be lighter and fluffier. So bakers started using chemical leavening agents like baking soda, which, if we were to use the actual chemical name, we would just call it sodium bicarbonate. It's made from soda ash, which at the time came from the ashes of sodium-rich marine plants like seaweeds, or it was made synthetically by reacting table salt, also known as sodium chloride, with other chemicals and minerals. Today, the chemicals needed to produce soda ash and baking soda also come from mines. But the baking soda you find on the supermarket shelves is the same compound that we've been using for almost 2 centuries. Usually, bakers would mix sodium bicarbonate and sour milk, which is full of lactic acid, and the reaction would produce bubbles of carbon dioxide, like the eruption in a science fair volcano. Those gas bubbles can puff up bread dough or cake batter, but the acidity of the sour milk isn't all that consistent, so neither were these reactions or their final baked goods. So the next leap forward in baking baking technology was in the 1840s with cream of tartar, also known as potassium hydrogen tartrate or potassium bitartrate. It's an acidic byproduct of wine fermentation, and when you mix it with sodium bicarbonate and some water, you get carbon dioxide bubbles. Cream of tartar helped make the chemical reactions in baking more consistent, but there was one big downside. The availability and price varied depending on the grape harvest in a given year. For a while, sodium bicarbonate and cream of tartar were sold in twin packets, which you added to the wet ingredients when you were ready to set off the reaction and stick your batter in the oven. This worked fine for bakers, but the supply of cream of tartar still wasn't consistent. Enter the chemist Ibn Horsford, who figured out how to make an acid called monocalcium phosphate from beef bones in 1856. Like the cream of tartar reaction, when you mix monocalcium phosphate, baking soda, and water, you get carbon dioxide bubbles. So Horsford mixed monocalcium phosphate and sodium bicarbonate together and then added some cornstarch to help keep everything dry and prevent early reactions. He marketed this concoction as Horsford's bread preparation, and voila, baking powder was born. During the 1880s, people realized they could extract monocalcium phosphate from mines instead, no beef bones required. And nowadays, most of the baking powder you'll find at the grocery store is labeled double acting. Like the name suggests, the sodium bicarbonate in double acting baking powder reacts twice. Once with an acid when the wet ingredients are added, and then with a second acid because of the heat of the oven. That way, your dough keeps rising while it's baking, and you get a fluffier product. However, some of these heat-activated acids can contain aluminum. Some people avoid double-acting baking powder because they're worried about the health effects of aluminum, although the CDC says the amount people consume in foods isn't enough to be dangerous. Either way, other double-acting baking powders are aluminum-free and use compounds like sodium acid pyrophosphate instead. So there you have it. Baking soda is just another name for sodium bicarbonate, while baking powder is sodium bicarbonate plus an acid or two and some cornstarch. An all-in-one chemical concoction just waiting for moisture and heat to get the reactions going. You can't substitute baking soda for baking powder unless your recipe also includes an acid, something like buttermilk, vinegar, or cream of tartar. So next time you bake a batch of chocolate chip cookies, remember to thank chemistry for that fluffy, chewy goodness.
Now, a lot of people say baking is just doing science experiments in your own kitchen, and this video's sponsor, Mel Science, is perfect for your at-home experiments. Mel Science helps bring science to life through fun, hands-on experiments. You know science is fun because you're watching SciShow. It's about discovery and asking questions with curiosity, all of which comes super naturally to kids. Mel Science sent us a few different kits, and I got to experiment with the luminescence one. I got to play with the luminescence kit in our studio, and it was very easy to follow along with, and we had a ton of fun. I got to play with some invisible ink, and we learned about fluorescence while making a glowy nightlight. Through virtual and augmented reality, you and your kid can get excited about conducting serious experiments and learning about their world. And Mel Science subscription boxes come with detailed explanations of the experiments so you don't miss a thing. If you're looking for a holiday gift, Mel Science is offering 50% off the first month of any subscription to SciShow viewers. Just click the link in the description down below and use the code SciShow at checkout. When you've got Mel Science, you don't need to fulfill your experimental urges in the kitchen. You can keep the cooking simple and just microwave your food. Now, if you're worried that the microwave is secretly a nutrient zapper, fear not. Here's why microwaving isn't as unhealthy as you might have heard.
The microwave is a marvelous invention. It's a quick, convenient way to heat up plenty of foods, from frozen dinners to leftover soup. But that makes a lot of people question how good it is for you. Do microwaves change the nutritional value of food? The short answer is yes, they do. But so does any other method of cooking. And actually, cooking food in the microwave gets rid of less of some nutrients than other methods like baking or boiling. When you preheat an oven, coils of wires heat up and then transfer that energy to air molecules, so they're moving around more. That motion is heat energy. And when you stick a frozen pizza in, the air molecules bump into the food and transfer heat from the outside in. Microwaves, on the other hand, cook food using electromagnetic radiation. The waves are changing electric and magnetic fields, so they especially affect molecules like water that are polar, with different charges on different parts. When you're microwaving your leftovers, the polar molecules keep flipping around to line up with the changing fields and heat up. The microwaves go through your whole burrito, so the center reheats at basically the same time as the outside. But the air doesn't really change during the microwaving process because those molecules are mostly non-polar. When people are worried about the nutrients in their food, they could mean all kinds of things. There are carbohydrates and proteins, or stuff like vitamins.
compounds that we have to eat because our bodies can't make them independently. All of those chemicals change when they're microwaved, but they don't change much differently than they would with other cooking methods. For example, heat can change proteins in a way that makes them easier to digest. There are some differences though. Like, microwaves can heat up things much faster than other appliances. That matters for the vitamins in your food, which break down more the longer they're exposed to heat. Vitamin C, for one, is particularly sensitive to heat. So a faster cooking time means that more of it sticks around. Some vitamins also tend to dissolve in water, so if you're boiling your veggies, those vitamins get pulled into the liquid. But microwaves avoid that problem too. A group of researchers in China took a closer look at cooking broccoli in different ways and measured its vitamin C content, along with some other nutrients. They reported the results in 2009. Boiling the broccoli led to the loss of 33% of its vitamin C. Stir-frying took away 24%, while microwaving only led to a loss of 16%. Steaming was actually the most efficient method, and hardly any of the vitamin C went away. But the microwave was in second place and not too shabby. So arguably the most convenient cooking tool in your kitchen is also one of the best ways to keep at least some of the vitamins locked in your food. And it makes popcorn too.
So microwaving can retain more nutrients than other cooking techniques like stir-frying. But how do those cooking techniques compare when it comes to retaining other stuff, like alcohol? Once again, Olivia has the answer.
You've probably heard that it's no big deal when a cake recipe calls for some rum or you add wine to a gravy for your turkey because it'll just boil off. And that's partially true. Some of the alcohol will get cooked out, but usually not all of it. The process of losing the alcohol depends on a few factors, so you can't assume that it'll all be gone by the time the dish is done cooking. It makes a lot of sense that alcohol would evaporate out of food that's being cooked, since ethanol, the drinkable kind of alcohol, has a fairly low boiling point, just around 78.5 degrees Celsius. Generally, you cook food at a lot higher temperatures than that. But all the alcohol in the dish doesn't just evaporate as soon as it hits its boiling point. It takes time. You'd have to boil a typical can of beer, for example, for 30 minutes to make it non-alcoholic. Plus, different recipes call for different cooking styles and even different cooking utensils, which all make a difference. In a study published in the Journal of the American Dietetic Association, researchers tested different recipes to see how long the booze stuck around. When they boiled a sauce with alcohol in it and then removed it from the heat, it still had 85% of the alcohol in it. On the other hand, a pot roast simmered at 85 degrees Celsius for 2.5 hours retained only about 6% of the alcohol. So both heat and time can contribute to the burn-off when you're cooking on a stovetop. But there's another factor too. The researchers did a few tests where they simmered orange burgundy chicken at 85 degrees Celsius for 10 minutes in 2 different sized pans. And there were huge differences in the amounts of alcohol left over. One pan was 30.5 centimeters in diameter, and the other 25.5. The researchers didn't state the depths of the pans in their paper, but the pans probably heated the food in similar ways. Basically, the main difference was that the chicken dishes had different surface areas that were exposed to the air in the room. And the wider pan with more surface area seemed to help more alcohol evaporate, retaining around 10% instead of around 60%. So if you're still tempted to cook with alcohol, don't be surprised if you end up a little bit tipsy after dinner. If you want to avoid putting alcohol in a dish at all, maybe stick with a flavor substitute like a juice, syrup, or extract.
Ultimately, the best way to prepare food comes down to what food you want to eat and what's important to you. If you value the flavor that comes from cooking with alcohol, then the best cooking method might come down to a combination of how much time you have and what kind of alcohol and cookware you have in the house. If you're more nutrient conscious, then microwave or steaming might be the way to go. And if you have a hankering for chicken or pig, any kind of food prep is better than none. And regardless of which way you choose to prepare your food, if you add some salt, it will probably taste all right in the end. Here's what makes that small addition so powerful.
Salt! It's kind of a superhero. Without it, French fries are bland, potato chips are boring, chocolate chip cookies lose their pop. And that's because salt doesn't just make things salty. It has lots of effects on flavor perception. In fact, if you're thinking about a spoonful of sugar helping the medicine go down, just a pinch of salt actually might work better. At the most basic level, humans like salt because we need it to survive. Salt, as we know it, which is usually sodium in the form of sodium chloride, is an essential nutrient. You use sodium ions ions for everything from communication between your neurons to managing your blood pressure. But your body can't just make sodium from scratch. It's an element, and you are not a star. So you have to get at least some of it from your diet. And since there isn't usually much salt lying around unless you live near the ocean, it makes sense that we evolved a taste for it to make sure we get enough. In 2010, researchers confirmed that we mostly taste saltiness thanks to epithelial sodium channels, which are basically pores that let sodium ions into the taste receptor cells in your taste buds. Those cells then signal your brain that something's salty. But weird as it might sound, salt actually makes things sweeter because it reduces your perception of bitter flavors. Studies have found that salt is actually better at reducing bitterness than sugar. Scientists don't have the mechanism for it completely figured out, but research suggests it involves both your tongue and your brain. Most of the bitterness blocking happens in your taste buds, where it's thought that the sodium might interfere with the binding between bitter compounds and their taste cell receptors. Salt also reduces other unpleasant tastes, so flavor chemists think it influences other taste cells too, somehow. But researchers have also found that if you're given salt and a bitter compound in such a way that they don't mingle on your tongue, you still perceive the overall flavor as slightly less bitter. That suggests that some of the anti-bitterness effect comes from how your brain interprets multiple taste signals when they include saltiness. Salt may also enhance sweetness more directly. We know that in mice, at least one of the proteins that pulls sugar into taste receptor cells can't do its job without sodium, so a dash of salt could mean an extra burst of sweet. Salt can also make things taste better by making them smell better. When you add salt, its ions are attracted to some of the available water in the food, and that makes it easier for volatile compounds, molecules that evaporate quickly and often contribute to something's aroma, to escape into the air. These compounds may not hit your tongue, but they still contribute a lot to your perception of flavor. Salt also seems to do things to make food more enjoyable, although scientists can't really explain them yet. For instance, volunteers in a 1985 study said that salted split pea soup was not only saltier, sweeter, and less bitter than the unsalted version, it was also thicker and fuller, altering what food scientists call mouthfeel. That one single ingredient transformed the whole dish, though honestly I would not want pea soup without any salt in it. That sounds bad. So if you're not happy with your dinner, there's a good chance that reaching for that salt shaker will help, which is why it's right there on the table.
Salt may be the great equalizer for food preparation. If you're looking for more tips from science to spruce up your cooking, you can watch our previous video with 7 more ideas to impress your dinner table company. Thanks for watching.